I can understand it. about the second simulation.
Okay.
So it's can I choose one of the ends could be fixed and the other end is free to the farm?
Yeah.
So
Yeah.
that's okay.
Yeah.
Okay.
Perfect.
I want to make sure if it's right or
Oh yeah. So the idea was to kind of change the boundary conditions.
yeah.
Because when you like for in your case you remove one of the fixed constraints, it's gonna have a totally different
Yeah.
information. So, yeah.
Thank you. Well,
Okay, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good to hear. All right, so this is the second lecture of week 9. So today, the main plan for today is to do an example for a quadratic interpolation. So we spent the entirety of last class going over this this algorithm for optimizing function using quadratic interpolation. So it is quite an involved algorithm. There's quite a lot of parts to it, and so today what I wanted to focus on was just doing an example so that you can kind of see it all in action. So the example today is a good kind of chance for you to kind of see what I'm kind of expecting on the homework. So the homework, one thing you'll notice for the homework is that I'm giving you these functions to optimize, and I want you to do it 2 ways. And so on one hand, I want you to work out the optimization by hand. And so I want you to execute all the calculations and the kind of the steps of the algorithm, doing it by hand. And the point of that is just to make sure that you kind of see kind of how the algorithms work. And because it's one thing to kind of read these algorithms and to just kind of implement it in MATLAB, but you don't really get a good sense of how they're actually working if you don't kind of work it through by hand. So we'll do that today. So we'll do one example by hand, and then I'll show you how it's implemented in MATLAB as well. Okay. And then if we have time today, I'm going to go ahead and move on to the next topic, which is called direct root. Okay. Okay, so one announcement, before we begin today, I am making an adjustment on the homework. So like I mentioned on Tuesday, the homework is very lengthy. It is going to take you guys a while to do it. So I'm shortening it a little bit. And so I'm taking out problem 5 on the homework. So problem 5 on homework 4 has to do with direct root methods. So I don't think we'll be able to get to direct root methods until next week. And so I don't really want to rush you guys into, learning something new and then applying on the homework right away. And so I'm going to take problem 5 and then make it part of the next homework. So I'm going to send an announcement for it after the class today. But just letting you guys know now that, for the homework 4 that's due next Friday, you only have to do problems 1, 2, 3, and 4. Okay. Okay. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. All right, and so we were going over this idea of using interpolation to optimize a 1D function, okay? And again, this is all within the category of nonlinear programming, okay? So just to kind of refresh your memory, okay? We're kind of, the algorithms that we're doing, in this whole unit is, it'll kind of feel like we're kind of tying one hand behind our backs. So we are developing all these algorithms to work with, where we only are able to take evaluations of the objective function. Okay. And in particular, what this means is that we're not able to take any derivatives. Okay. So how do we optimize an objective function, or how do we obtain the optimal design parameters without being able to take derivatives? Okay. So there's lots of different ways that you can do this. So with interpolation methods, we're basically telling ourselves, okay, we can't take derivatives of the original objective function, but what if we make up a new function? So we create a new one that represents our objective function, and that one we can take derivatives. Okay. And remember that new function that we're creating is called the surrogate function. Okay. So since this surrogate function is basically something that we're making up, we have kind of full control over, how we define it and how we take derivatives of it. Okay. Okay. And so in particular, the surrogate function that we're working with, for our purposes is a quadratic function. Okay. So remember, the reason we're picking a quadratic function is that it's the simplest polynomial that you can have that has a clearly defined minima or clearly defined maximum. Okay. So our quadratic function is given by a plus bx plus cx squared. Okay. Where now our goal has slightly shifted. So, by saying that we're going to use a quadratic function here, we want to make sure that our quadratic function or our surrogate function is a close approximation of our original function. Okay. And so what that means is that these three coefficients, a, b, and c, we want to choose their values such that this surrogate matches our original objective function as closely as possible, at least within the neighborhood of the minimum. Okay. So that's kind of the general idea. And once we have good values for A, B, and C, then we can just simply take the derivative of this function, solve for X, and that's going to be our optimum. Okay. But the challenge here is no longer kind of, it's shifted a little bit. Our challenge is not really finding the optimum of our original function. It's making sure that our surrogate function matches the original one as closely as possible. Okay. All right. And so this algorithm kind of proceeds in two phases, right? So phase one, is to find the optimal step. Okay? Because if you recall from Tuesday, the way that we're going to solve for A, B, and C is we're going to make 3 evaluations of our objective function at 3 separate locations. Okay. And so by step length here, step length basically is going to tell us where, which locations we're going to evaluate our objective function. Okay. Because we evaluate the objective function at 3 locations in this space. We evaluate it at x is equal to 0. We evaluate it at x is equal to t. Okay. Where t here is the step length. And then we evaluate it at x is equal to 2t. Okay, so those are the 3 locations. Once we evaluate the objective function at these 3 locations, we obtain 3 function evaluations. And so we call this f sub a. The second location we call f sub b. And third location we call f sub c. Okay. Okay, so these 3 f's these are our function evaluations. And this is the original objective function. Okay. Okay. And then based on these function evaluations, we can solve for the coefficients of our polynomial. Okay. And so we went over this last time. So the coefficients of our polynomial. So we'll start with a. So a here is just simply going to be f sub a. Okay. That's simplified for us because we're evaluating the objective function at x is equal to 0. Okay. B here is going to be 4 fb minus 3 fa minus fc all over 2t. And then c is fc plus fa minus 2fb all divided by 2t squared. Okay, And then once we have our values for A, B, and C here, X min, which is our approximation for the optimum of our objective function, is simply just minus B over 2C. Okay. Yeah. Yeah, we went over this last time. So that was from the last. I think last time I used slightly different notation. So instead of FA, I use F of 0. So if you look back in your notes, it may look like, yeah. All right. So that's kind of the general idea with this phase right here is to get kind of a first good guess of your surrogate function. Okay. All right. But the main thing that we're doing here in step A is to make sure that our step length here is adequate. Okay. And to make sure that our step length here is adequate, we have to choose basically we have to check the relative magnitudes of FA, FB, and FC. Okay. And so if you remember from last time, there were kind of three conditions based on, whether FA is greater than FB, which is less than FC. And so, there's kind of three conditions there on whether, we need to either make our step size bigger, make our step size smaller, or, making sure that it's just right. Okay. So I'm not going to write those three rules down again, just because it's a bit lengthy, but, just know that, for this phase right here, we're going to go through several iterations of testing out our objective function, computing the coefficients, and seeing whether we need to adjust our step size. Okay. And so we're going to repeat this step as many times as needed until our step size is adequate. Okay, so that's phase one. So phase one is to kind of just get the surrogate into a decent spot. Usually sometimes at the end of phase one, you might be done. So after phase one, you might get a situation where your surrogate is already a good match and you're able to find the optimum from there. But odds are, after phase one, the results are not going to be perfect just yet. So you need to kind of refine the surrogate. But that's in phase two. Okay. All right, any questions on phase one? Okay, good. Okay, and then we enter phase two of the algorithm. Okay. Phase two, we're going to refine our surrogate. Okay. So this whole method or this whole algorithm kind of banks on the fact that, our surrogate function is a good approximation of our objective function. Okay. Okay. And so the way that we check that is we check the following metric. And so what we do is we evaluate our surrogate function, f tilde, at x min. Okay. So this is the x min that we computed at the end of phase one. Okay. Minus f of x min. Okay. So basically what you're doing here is you're evaluating both your surrogate function and your original objective function at the same x min. Okay. And hopefully, what you should get is that these two should be pretty similar. Okay. And if you divide that by f of x min, just to normalize it, okay, take the absolute value, this should be less than some small threshold here. Okay. So this is some small number. Okay. So, you can kind of set what that small number is. Usually I set it to be about 0.05. But kind of the smaller that you make that number, the more accurate your results are going to be. Okay. Okay, so odds are, when you compute this quantity at the end of phase one, it's going to be not very good, and so it's gonna be pretty inaccurate. Okay. Okay, so in this phase, we basically recalibrate our surrogate by choosing different evaluation locations. And so in this step, we do something a little bit clever. So we're just, we're trying to make use of the work that we've done already. Okay. Because by computing this metric above here, you'll notice that we've evaluated our objective function at an additional location, right? So x min most likely is not going to be part of, you never evaluated that in step one, okay? And so in phase two, we're gonna take advantage of that fact and use this in our calibration. Okay, so we're going to incorporate f of x min. Right, so we're going to incorporate that point into recomputing our surrogate coefficients. And the reason we're kind of doing this is that, these algorithms, we want to evaluate our objective function, as little as possible. So if we can kind of reuse something that we've done already, that's kind of the optimal thing. Okay. Okay. And so this this step right here, this was kind of the very last thing that we went over last time. So I'm just going to scroll back up here really quickly. Okay. And so if you remember at the end of class, we went over these 4 rules right here. And so these 4 rules will tell you how to best adjust your surrogate function based on the values of f of x min and fa, fb, fc. Okay. Okay, so I'm not going to write these down again just because it's long, but that's basically the rules that we're going to use for this. Okay. All right. And then once you do that, once you recalibrate the surrogate, then you can recompute the coefficients a, b, and c. Now, you have to be careful here because the formulas for A, B, and C are going to be different in phase 2 compared to phase 1. Okay. In phase 1, when we computed the values for A, B, and C, that was when one of our points was x is equal to 0. So that actually simplified our function quite a bit. And we had the benefit of all the points were kind of equally spaced apart. So they're all spaced apart by the step size. Once you kind of start recalibrating the surrogate, you kind of lose that assumption. And so we need new formulas for A, B, and C in phase 2. Okay. So there's no way around it. These equations are kind of they're a freaking mess. There's no other way to say it. And it's, we're doing a solution to a three equation, three unknown system of equations, and there's no symmetry or there's no pattern for us to kind of take advantage of. So just kind of be prepared. But just know that most of the time you're not computing these equations by hand. You're going to type this into the computer once in MATLAB, and then MATLAB's going to do these computations for you. Okay, so it's going to look really scary. Just kind of warning you guys ahead of time. Okay, so these formulas I didn't give you last time, so these are new. So we didn't really get a chance to finish talking about phase 2 last time. Okay, so our formula for A is now FA times XB times XC multiplied by quantity XC minus XB plus FB times XC times XA times XA minus XC plus FC times XA XB times XB minus XA. And that's just the numerator. All right, and then the denominator here is XA minus XB multiplied by XB minus XC multiplied by XC minus XA. All right, so a little bit more complicated than before. So before in phase 1, our formula for A was quite easy. Our formula for A was just FA, just the evaluation of our function at x is equal to 0. But now it's a little bit more complicated. Okay. Now we have our formula for B. All right, so after you kind of get over the initial shock of A, then formulas for B and C are a little bit easier. Okay. All right, so for B, we have FA multiplied by XB squared minus XC squared plus FB multiplied by XC squared minus XA squared plus FC XA squared minus XC squared, or XB squared, excuse me. And then the denominator is the same as above. So we have XA minus XB multiplied by XB minus XC multiplied by XC minus X. All right, now we have one more formula to go over for C. And I'll try to keep it so that they're all on the same screen. Okay, so our C coefficient here. So this is our quadratic term in our surrogate function, right? Is equal to. So we have a minus sign out in front here. So don't forget the minus sign when you're doing problems. FA multiplied by FXB minus XC plus FB multiplied by XC minus XA plus FC times XA minus XB. And then our denominator here is the same. So XA minus XB, XB minus XC, XC minus XA. All right. So again, these look really scary because they are really scary. If you're punching this in by hand, it's very easy to make a mistake on these types of equations just because there's just so many terms here. But remember these algorithms are designed to be computer algorithms. Um, you know, and so the idea is you put these equations in your MATLAB code once, you put it inside a for loop, and then MATLAB will kind of compute these automatically for you. MATLAB will do it perfectly as long as you input the formula in MATLAB perfectly as well. Okay. All right. So that's phase two. So phase two, we're just kind of recalibrating our surrogate until it's as good a match of our original function as much as possible. Okay. So we're going to repeat phase two. We're going to repeat phase two until our convergence metric is satisfied. Okay, and then just to kind of remind you, our convergence metric was this guy right here. Okay? So our convergence metric is we're evaluating our surrogate function at a certain point. We're evaluating our original objective function at our best guess for the minimum. And if those two are matching, then we're good. Okay. All right. Any questions on phase two before we jump into an example here? Okay. All right. So let's do an example so you can see kind of all this in action. So, interpolation algorithm, pretty complex. So there's kind of no way around it. Even just doing a quick recap of the algorithm took us almost 30 minutes to do. So yeah, not an easy algorithm here to execute. Okay, so for this example, let's find the minimum of the following function. So we have f of x is equal to x to the fifth minus 5x cubed minus 20x plus 5. Okay. So that's our original objective function. And so we're going to use quadratic interpolation. And this problem is going to give us an initial step size as well. So this problem says to use an initial step size of 0.5. Okay. The problem statement is very short. So, for these optimization problems, all we really need is just the objective function. Sometimes we're going to need a little bit extra information about the algorithm. So in this case, we're given the step size, and then we'll just say, just let it go. Okay. So this example here is a good, a good kind of demonstration of kind of what a lot of the work on homework 4 is going to do. So problem 3 and problem 4 and homework 4 are going to be very similar to this. Okay. So let's go ahead and start our algorithm here. So we need to start with phase 1. Okay. So even though we're given an initial step size here, we don't really know yet if that step size is adequate for the problem. Okay. Okay, so we want to adjust our step size first. That's phase 1. Okay. Okay. So the way that we are going to adjust our step size is we're going to evaluate our original objective function at 3 locations based on the step size. Okay. So we're going to evaluate it at x is equal to 0, x is equal to t, and x is equal to 2t. Okay. All right, so for our given step size, that means we're going to evaluate at f of 0. We're going to evaluate f of 0.5 and f of 1.0. All right, so let's go ahead and plug these x values into our original objective function and compute their values. Okay, so f of 0 is going to be 0 raised to the 5th power minus 5 times 0 cubed minus 20 times 0 plus 5. Okay, and so what we get from that is just 5. Okay, so everything with 0 goes away. We're going to plug in 0.5 for the second step. So we have 0.5 raised to the 5th power minus 5 times 0.5 cubed minus 20 times 0.5 plus 5. Okay. So for this one, you're going to need a calculator for this, unless you can do 0.5 raised to the 5th power in your head, which I cannot. So I'm going to go ahead and plug this into a calculator. And what I get is minus 5.594. Okay. And then finally, we have f of 1.0. So I'm not going to write out the whole equation here. You can imagine we're plugging 1.0 in for x, and what we get from this is minus 19.0. Okay. All right. And so let me go ahead and label these. And so this first one here, at when we evaluate it at x equal to 0 is going to be fa. The second evaluation is going to be fb, and the third evaluation is going to be fc. Okay. All right. So since, right, if we look at the relative values of these all three of these evaluations, we can see that FA is greater than FB, which is greater than FC. Okay, so we have basically our value of the objective function is descending at every iteration here. Okay. If you go back to our original, our kind of go back in from your notes from Tuesday, you'll see that this is a specific case right here, which tells us that our step size is too small. Okay. So we need to increase our step size here in order to, in order to get our surrogate to work. Okay. Okay. So at this point, you can kind of choose yourself how you want to increase the step size. So if you want to be a little bit, I would say conservative, I guess you can only increase it by a little bit. So maybe you only increase the step size by like 10%, and then you just kind of check everything again. Okay. So that would be kind of the slow and careful way to do it. But of course, by doing so, you kind of are at risk of kind of doing too many function evaluations. Okay. So if you're really far off, and so if this step size is nowhere near where it needs to be, if you kind of increase the step size a little bit too carefully, it's going to take you a lot of iterations before you actually arrive at the perfect step size. Okay. And so we ain't got time for that. And so, we only have about, 40 more minutes left in class. And so we're just going to speed this up a little bit. Okay. So let's try doubling the step size. Okay, so by doubling the step size, our step size is now 1.0. Okay. And so our three locations where we're going to evaluate our objective function here are going to be x is equal to 0. That one doesn't change. X is equal to 1, and x is equal to 2. Okay. All right, so one nice thing about doubling the step size here is that, we can actually reuse some of the results from before, right? And so if you look at the three function evaluations that we did, we've already gotten two of them that we need for this step, right? And so we need f of 0. Okay. So we already know from step 1 that f of 0 is equal to 5. Next thing we need is the evaluation of the objective function at the midpoint. And so our new midpoint was actually the same thing as our old endpoint. So we can just reuse the results from above. So both of these are from above. So the only new one that we have to evaluate here is x is equal to 2. We have f of 2. And so we're going to plug in 2 into the objective function. So we have 2 raised to the 5th power minus 5 times 2 cubed. Minus 20 times 2 plus 5. Okay. All right, so we plug all those in and we get minus 43. Okay. All right, and then based on these results here, what we can see is that fa, which is the function evaluated at x is equal to 0, is less than, or greater than, I'm sorry, is greater than fb, fb being the function evaluated at the midpoints, okay, which is still greater than fc. Okay. So this tells us that our step function is still too small. Our step size is still too small. So actually, in this case, taking an aggressive step, taking the step to double our step size is actually a good move because, we still haven't reached that point yet where our step size is small. Okay. So let's double our step size again. Okay. And, again, I'll make the note here that normally you're not going to be this aggressive. So doubling the step size with each iteration is pretty aggressive. And so, I don't know if you remember from a couple weeks ago, a lot of these algorithms have this idea of using a step size. And so if you increase the step size a little bit too rapidly, a little bit too aggressively, you may miss some information. So for this problem, I know it's going to work out because I've done it already, but just kind of be careful when you're implementing things in math. Okay. Okay, so our new step size after doubling again is going to be t is equal to 2. Okay. So once again, we have our three function evaluations. We have x is equal to 0. Our midpoint is now x is equal to 2. And our endpoint is now 4. Okay. Okay. So our evaluation at the origin is still the same. So f of 0 is still going to be 5. Okay. We evaluated f of 2 in the last step. So f of 2 is minus 43. Okay. And so the only new evaluation we have to do at this point is f of 4. Okay. Question. Which in this case is 629. All right. So if we look at the relative values of these 3 points right here, we can see from these two, f of a or fa is greater than fb. Okay. But when we evaluated our new fc, we can see that it's greater than fb. Okay. In fact, it's very much greater. So, you can make the argument that we were a little bit too aggressive and we kind of overshot where we needed to be, but that's okay. But the conditions for our steps or the conditions to end phase 1 are exactly these conditions. So you go from a high value to a low value back to a high value. Okay. So this tells us that a step size of 2 is adequate, or it's at least a good starting point to move on to phase 2. All right. So now that we have a good step size, we can compute our coefficients of our surrogate. Okay. So this is the formulas for A, B, and C for phase 1. Okay. So A is equal to just FA. Okay. And so we plug in FA in this case. FA is just 5. B is equal to 4FB minus 3FA minus FC, okay, all divided by 2T. So we go ahead and plug in all the values for this one, and what we get from this is a minus 204. Okay. And then C is FC plus FA minus 2FB divided by 2T squared. We're going to plug in everything for this as well, and we get a value of 90. Okay. Based on the function evaluations that we did, right above this. Okay. All right, so we plug these 3 coefficients in, and so we get our surrogate function. Okay. So f tilde of x is equal to 5 minus 204 times x plus 90x squared. All right. So after all that work, we have our first surrogate function. Okay. Now remember, now that we have the surrogate function, we can kind of do whatever we want with it. So this surrogate is something that we kind of made up during this algorithm. So we don't have the same limitations on this. So we can take the derivatives of this. Okay. Okay. So let's go ahead and take the derivative of this. And so we're going to take df tilde dx. Okay. This is just a simple polynomial here. So we are just going to, just take this derivative. We have a minus 204 plus 2 times 90 times x. Okay. We set it equal to 0. Okay. This x now becomes x min, which is our guess for where the optimum is. Okay. And so we solve for x min. That's equal to 204 divided by 2 times 90. Okay. Which is exactly the same as minus b divided by 2c. Okay. So you don't have to actually take the derivative. You can just plug in the formula minus b over 2c. But I just kind of wanted to remind you where that formula came from. Okay. And so we plug that in and we get 1.135. All right, so that's our first guess for the minimum. Okay. All right. So our next question is x min equal to 1.135? Is this a good approximation for the minima of our original objective function? All right, so let's go ahead and check our convergence criteria, okay? We're going to take f tilde of x min. Okay. So we're going to evaluate our surrogate function at its minimum, okay, minus our original objective function, a value at the same point, okay, and then take the percent difference between the two, okay? All right. So let's go ahead and plug these in. Okay. So first thing, we're going to evaluate our surrogate function at our proposed minima here. Okay. So we're going to plug in 1.135 into our surrogate function, which was 5 minus 204 times x plus 90x squared. And so if we do that, we get minus 110.9. Okay. And then for the other part of this equation here, we're going to plug in that same x is equal to 1.135 into our original objective function. So that's the one we kind of started with in the original problem. Okay, so our original objective function, just to kind of refresh your memory, is f of x is equal to x to the fifth minus 5x cubed minus 20x plus 5. Okay. So if we plug in 1.135 into this equation here, what we get is minus 23.13. Okay. So right off the bat, you can see the two values here. Right, so one of them is giving you a value of minus 110. The other one is giving you a value of minus 23. So, just intuitively, you can see that these are not even close. Okay. And so this is telling us that we need to refine our surrogate. Okay. If you're curious, if you wanted to plug into this equation up here, we get 3.8. Okay. So that means that our guess right now is 380% off. Okay, which is pretty far, right? So we're not that close yet. Part of the reason we're starting so far is because we were so aggressive in phase one. Every time that we had to increase the step size, we did it by doubling it. And so we're kind of in a situation right now where maybe we went a little bit too far with increasing our step size. Okay, but that's okay. That's what phase two is all about. So phase two is all about how can we refine this surrogate to make it better. Okay. All right, but that's phase one in a nutshell there. So phase one, we've settled on a step size. We're moving forward with 2.0, and then we'll go. Okay. Any questions on phase one? Okay. All right, so let's go ahead and move on to phase two. Okay. Phase two, we're going to refine our surrogate. Okay. So in this phase right here, we're going to use our 4 rules, to determine how we're going to refine our surrogate. Okay. Okay. So the information that we're going to need is we're going to need the values of all the x's at this point. Okay. So our xa is 0. Okay. Xb is 2.0. Xc is 4.0. Okay. So that was our original 3 locations that we picked, when we picked our step sizes in phase one. Okay. The other piece of information we need is our current guess for our minima. Which we know from the last step was 1.135. Okay. Okay, so the other thing that we're going to need is we need to evaluate our objective function at these three locations. Okay, so this again was from phase one, so we're just going to copy that information down here. Okay, so FA, which was f of 0, is 5. FB here is minus 43, and then FC is 620. Okay. And then the last thing that we have, this is the one that we just computed. We have our original objective function evaluated at x min. So we just evaluated this. This was minus 23.1. Okay. So based on all of these all this information here, we can go ahead and decide how we're going to refine our survey. Okay. Okay. So to do this, you need to go to the 4 rules, right? So that was the kind of thing that we did very last thing last Tuesday. I flashed it really quickly today. Okay. Okay. So if we go back, I'm just going to go back really quickly. So our 4 rules for all of these guys right here. Okay. So depending on the value of x min relative to the step size, and depending on the value of x min f of x min compared to f of t, which is fb, then this tells us what we need to do. Okay. Okay. So let's come back down here. Okay. So in our case right here, x min, which is 1.135, is less than our step size t. Okay. So remember, our step size t is 2.0, x min is 1.135. Okay. All right. But f of x min in our case is actually greater than fb. Okay. Because f of x min in this case is minus 23.13 and fb is minus 43. Okay. Okay. So what this tells us is that we're going to, if we go back to our 4 rules, this means we're going to discard the old XA and FA. Okay. So we're going to discard X is equal to 0 and F of 0 as well. Okay. Yeah.
Isn't it also obvious it's not a minimum if the evaluation at the minimum is greater than the evaluation of?
Yeah. Yeah. We were a little bit too gung ho with the step size. So yeah. In this case, yeah. It is a bit obvious just based on that for sure. Yeah. Mm-hmm. All right. So let's go ahead and discard that. And so according to our rules up there, what we're going to set now is that our new XA is going to be X min. Okay. And our new FA is going to be F of X min. Okay. So XA is going to be now 1.135. FA here is going to be a minus 23.13. Okay. Everything else is going to stay the same. So XB is going to be still 2.0 and FB is a minus 43 and XC 4.0 and FC is still going to be 629. Okay. So these two stay the same. Okay, so now that we have our new values here, we can recompute A, B, and C. Okay. And just a reminder, remember, the formulas that we use for A, B, and C are different in phase 1 versus phase 2. So make sure you use the phase 2 versions. Okay. And that's actually really important in this case because we're no longer using x is equal to 0. Okay. Okay. And so if we do that, then our new values for our coefficients are going to be very different than before. So our A here is going to be 288. Our new value for B is going to be minus 417. And our new value for C is 125.3. Okay. So our surrogate function now, we've recalibrated it. F tilde of x is equal to 288 minus 417 times x plus 125.3 x squared. All right. So based on this function right here, we can compute a new x min. Okay. So x min is just going to be a minus b over 2c. And what we get from that is 1.661. Okay. So quite a bit different here, right? So we move from about 1.1 to about 1.6. Okay. Okay. So now that we have a new value for x min, let's check convergence one more time. Okay. We're going to check convergence. We're going to have absolute value f tilde of our new x min minus f of x min divided by f of x min. Okay. All right, so we plug these in. Make sure you're using the new surrogate too. Okay. So this value we plug into our surrogate model, we get minus 59.7. And we get this one here. This is going to be minus 38.37. Okay. So not quite there yet. We're getting closer though, so that's encouraging. So compared to our the end of phase 1 here, we see a big improvement. Okay. And so we compute this and we get 0.556. All right, so we're less than 1. So that's good. Always a good thing. Okay. So this is better, but not good enough. All right, so we're going to refine one more time. So with this last refinement here, I'm going to go a little bit quickly just because I want to make sure I have enough time to go over the code. But you know, it's going to be just kind of a repeat of kind of what we just did. Okay. Okay. So once again, we're going to check the value of x min relative to our step size. Okay. And so our new x min here is 1.661. Our step size is still 2.0. Okay. So in this case, x min is still less than t. Okay. Next thing we're going to check is f of x min versus fb. Okay, so our new f of x min, so that's our original objective function evaluated at our new guess for the minima. And so that is a minus 38.37, okay? And FB is minus 43. Okay. So in this case, f of x min is greater than FB. Okay. And so this is actually the same case that we did that we had before. Okay. So we're going to discard our old FA and XA and replace with f of x min and x min. Okay. All right. And so our new values for all these is we have FA is equal to minus 38.37, XA is equal to 1.661. Okay. FB and FC are still the same. So FB here is minus 43, XB is 2.0, FC here is 629, and XC is 4.0. Okay. So again, these stayed the same. Okay. So based on these values here, we can recompute A, B, and C. Okay. And so if we recompute the coefficients we get, A is equal to 480.92. B is equal to minus 560.94. And C is 149.5. Okay. All right. So our new surrogate model is f tilde of x is equal to 480.92 minus 560.94 times x plus 149.5 x squared. We get a new estimate for our x min. Okay. And so our x min in this case now is 1.876. All right. So once again, we're going to check for convergence here. Okay. We're going to pray that we struck gold this time. Okay. And so we have f tilde of x min minus f of x min divided by f of x min. Okay. So once again, at our new guess for x min here, we're going to evaluate our surrogate function and our original objective function. Okay. Okay. So evaluating our surrogate function at x is equal to 1.876, what we get is minus 45.29. And then we evaluate our original objective function, we get minus 42.3. Okay. So we're close. We're really close. And so if we compute the percent difference between them, we should see we get 0.071. So it's about a 7.1% difference. Okay. So is this good enough for convergence? If you ask me, if I'm doing this problem by MATLAB, I would say no. And so, if we're doing this in MATLAB, I would say, let's keep pushing it, let's keep iterating. If we're doing it by hand, I say this is plenty. We've done enough. We've done enough at this point, right? So in reality, I would probably push this until we get maybe about a 1%, 5% difference. But this is pretty good. Okay. And so, we're kind of in a unique situation here where our FB was actually so good, right? So if you recall, FB, which was F of 2.0, was a minus 43. Okay. That's actually still more minimum than, that's actually still smaller than what our current guess for X-min. So our minimum might actually be at 2.0, or at least very, very close to it. So, so if we iterate again, I think what you're going to see is that our guess for X-min is going to creep even closer to 2.0, and then we'll get even closer. Okay. All right. Any questions on this example here? Okay. All right, so for the last maybe seven minutes, let's go over the MATLAB code. So let me go ahead and share my computer screen here. Okay, so this code is available to you online. And so if you go to the file section of the Canvas page, you should see that we have I have codes for 1D nonlinear programming. This is going to be this is example 3 for quadratic interpolation. Okay. So we did, I did an example for, exhaustive search. And so here I call it unrestricted search. It's the same thing. I have another example code here for dichotomous search. So we didn't go over this in the class just because of time, but you're definitely free to use this as well. Okay. By the way, pro tip. So when you're working on the homework, and the homework asks you to implement a MATLAB code for dichotomous search or exhaustive search or quadratic interpolation, use these example codes. So I've written them in a way where you can take them and then just kind of small modifications to them to work on a new problem. That's kind of why I provided them to you guys is for you to use them. Right. And so, I would say that for this homework, you can take this code right here and maybe modify, okay, it's kind of a lot of modifications, but basically everywhere you see the objective function there, you have to modify it for the new, okay? Okay, but let's go over this code right here just so that you can kind of see how it all works, okay? So this code here solves the exact same problem that we just did, but in MATLAB, okay? So what you're going to see is that you're going to see phase 1, phase 2 of this algorithm, all the conditionals, all of the formulas just implemented in MATLAB, okay? And remember, the thing to remember with these MATLAB codes is to read it from top to bottom, okay? Because that's exactly how your MATLAB code is, or that's exactly how MATLAB's going to read your code as well, okay? Okay, so the first thing that we have here, so first thing, so I guess the first, if you're curious about these lines of code here, that's just to kind of clean up the workspace. I have these at the top of all of my codes, but the real algorithm starts right here, okay? Okay, so the first thing we need to do here is we need to define our step size. And so if you recall from the original problem, we had an initial step size of 0.5, okay? So that is our step size here. The next thing I need to define at the top here is our convergence threshold. So you can see here that I'm having a very strict convergence threshold here. So I'm setting the convergence threshold to be 1 times 10 to the minus 4, which is a 0.01% difference, okay? So this code here is going to continue, and so it's not going to be satisfied at a 7% difference. It's going to keep going. Okay, next thing we need to do is we need to define the initial 3 locations for forming our surrogate. So that's going to be XA. XA in phase 1 is going to be still 0. So actually, let me put this here. So this is start of the phase 1 of the code. Okay. XB is at the step size location, and XC is at 2 times that. And then here we're evaluating the objective function at those 3 locations. So remember, our objective function in this case is x to the 5th power minus 5x cubed minus 20x plus 5. So I evaluate it at XA, XB, XC. Okay. Okay. So now this is phase 1 of the algorithm. Okay. So remember, phase 1 of the algorithms, we want to adjust the step size until it is kind of perfect for our problem. Okay. So the first thing I'm checking here is see whether our step size is too big. Okay. Okay. So the conditions for this, if you remember, is if FB is greater than FA. So if the evaluation of our objective function is greater at the midpoint compared to our origin, then we need to make our step size smaller. Okay. So while this is true, okay. So a while loop is basically just it's going to repeat code until this condition here remains false. Okay. And so while this is true, we're going to cut the step size in half and then reevaluate our 3 points here. Okay. And so once we cut the step size in half, we reset the values of XA, XB, XC, and then we compute the objective function at those locations as well. Okay. And we do this until FB is less than FA. Okay. But the interesting thing about while loops is that if this condition here is false to begin with, then we don't even execute any of this code right here. Okay. So in this problem, we actually have a situation where, we don't even execute this code because our FB, is not greater than FA. Okay. Okay. So that's the part of the code which adjusts the step size to make it, smaller if we need to. Okay. So this section of code here is, making our step size bigger if we need to. Okay. And so the conditions for this is that if FB is less than FA and FC is less than FB, right? So remember, these are the exact conditions that we checked in the problem that we did, before. We're going to make the step size bigger. And so you can see here, I'm doubling the step size and I'm recomputing this. And this continues until this is not true. Okay. And so once you kind of get done with these two while loops, then phase one is complete. Okay. So let me go ahead and write that in here. Okay. And then we obtain our estimation of XMin and our surrogate model, or excuse me, our original objective function at this XMin. Okay. And then we compute our surrogate, and then we compute it from there. Okay. So we are out of time, so I don't want to keep you guys anymore because phase two will take a bit of time to explain. And so when we come back on Tuesday, we'll kind of jump right back into this. I'll explain phase two of the code right here, just so that you can kind of see how it works, and then we'll move on to direct root methods. So thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend. I have your exams today, so if you didn't pick up your midterm one yet, today is the last day I'm bringing it to class. If you don't pick it up today, then you have to come to my office, okay? So thank you guys. I hope you have a good weekend, and I will see you on Tuesday. Yeah. Oh, yeah.
Other question is, so we need to do like points, this, right?
Yes.
Upload and they go yes and not yes.
Yeah.
Okay, because I was thinking of using the local like the blocks.
Okay.
So to the paper you say, I don't know, like, and would that be like instantly then?
Say again. So two dots, or
No, like 3 blocks. Let's
Oh.
say German Shepherd, like
Yeah.
the little one and then a big one. So would it be like 2 or 3?
So you would so you just change the magnitude of the force.
Yeah.
So I would want to actually see the force actually going in a different direction of these, because if you just change the magnitude of the force, what you're going to see is that the deformation and stress, the value is going to change,
Mhm.
but the actual distribution is not going to change.
Okay.
So I actually want to see the distribution actually kind of change to
Okay, okay.
Yeah.
So what if I say then that the dogs like, okay, now, but would it make sense then to say that those, like, go left and right.
Yeah, that's fine.
Yeah.
Yeah, so maybe you have one case where the dogs are pulling, the handle's like this, right?
Yeah.
So maybe the dogs are pulling this way in one scenario, maybe another scenario they're pulling this way.
Okay.
Yeah.
So that would be.
That would be fine.
Okay, thank you.
Yep.